So, all right. So we'll get started. Good evening, everyone. Welcome. I could talk louder. Good evening, everyone. Welcome to the October meeting of the Astronomy section, Rochester Academy of Science. For those of you who don't know me, I'm Mark Mineridge, president of the Astronomy section of the Rochester Academy of Science. Thanks to everybody for coming. You have an opportunity to vote for me again in another month or vote me out next month. So with your permission, I will be your president in another 2 months, or to the end of the year anyway. Welcome, everyone.
As always, Brett fun to be the president.
Huh?
This is Joe.
Okay, I didn't catch it. Ken was telling a joke for those of you online. I didn't catch it. Anyway, here's tonight's agenda. We have a welcome, which is welcoming you now. We'll do some announcements, and then we'll have a feature talk by Alice Quillen, a professor of physics and astronomy at the University of Rochester on soft astronomy. Talk a little bit about asteroids and how they model that stuff. It sounds like a pretty interesting talk. So we'll start with, anybody here for the first time? This is the first astronomy section meeting you've been to. And I'm not going to embarrass you. All I'm going to ask you is what your name is and how you found out about us. What interests you here? Ellie? I saw Vicky with the globe. She's right in front of you. Yes. Went up to the site on the hayride. There's Dave. Awesome. Well, welcome. You're a fellow Ionian. I'm also an Ionian. There's a couple of people from the area are here tonight, so welcome. Thank you for coming. Anybody else first time they've been here? There's somebody way in the back. Okay, glad you found us. And your name? Oh, thanks for coming, Craig. How did you hear about us? What interests you here? Awesome. For those of you online that may not have heard that, he found astronomy as a kid, and he's rekindling it now that he's getting closer to retirement. So, as some of us are. So, welcome. Glad to have you here tonight. Anybody else that's first time here? Thanks, guys. Thank you for coming. Welcome. Okay, let's share. We'll share observing stories. If anybody has observing stories over the last month or so that you might want to share with us. Anybody do some observing in the last month that they want to share with us? Anybody online?
I'll share one.
Sure, Tom.
So I've been spending a lot of time in the brew house, and everything, and it's been a great experience. But the thing that's really interesting is I went to graduate school for astrophysics and then stepped away from it for 30 years. It's been a pleasure to be back at it again, actually working with imaging. How much has changed in 30 years is absolutely crazy. So a lot of my time has been spent sort of figuring out how to make the telescope do what I want it to do. I have one at home. Been a little bit of experience in the telescope in the brew house to do the same thing, but I'm nearly there. So that's been a great experience. So a lot of fun. Most recent work I've been doing has been on the elephant trunk. Got my 8 alpha subs in, and now I'm going to go back and get my breathe. I'll either choose to do sulfur 2, or I'll go for green and do the alternative.
Okay.
HA, and then the oxygen 3 on the other end. So,
All right.
Hopefully Sunday will be clear.
Well, good luck. Actually, tonight's a better night.
I should hope so.
Thanks, Tom. Anybody else want to share any observing they did over the last month or so?
We had about 4 sessions the strategy, we're out on the sidewalk with the scopes, they're looking on the deck.
Yeah,
Better,
Yeah.
moving on down on the underneath the wall, on the side.
underneath the lights on the sidewalk.
Could be back doing something like, we haven't started star parties yet, that's.
Next step doing star parties. Good. Look forward to doing that. I know there's people chomping at the bit to look at the sky. So thanks, Jim.
We're 35 people, we're not advertising. We're trying to experiment with diabetes. It's not working. It's hard to walk up and have cover. That's why we're.
Okay. I can do that.
I observed something this morning in the sky. Earlier today, I went to the station. So when it's close, it was a median EX 125 with a good mount on. I seen that. I went to the estate sale and I wondered how much they'd be asking. I put it to you, experts who know all about telescopes. How much do you think someone would charge for a used D?
Oh, how old is it?
125? How old would it be? About 5 years old.
$150.
Well, 1,200, 1,200, 400, 600 a year.
125?
$550.
This is a little pricey.
Yeah, I thought it was a little pricey.
Seems a little pricey.
It's a little pricey.
You
But
can,
then if I go tomorrow, sometimes they drop the
Yeah.
prices on the second.
yeah, you can get a brand new Orion 8-inch Dobsonian for $450. So you get a lot of aperture, you got a lot of flexibility. If somebody's looking for a scope, I say, if you got a with an under a $500 budget, I'll point them in that direction because that's what you get a lot of scope and not a lot of cash for it. But you don't get the you got to figure out where you're going, but that's with the go-to. But I find go-to with anybody new is a little hard to coordinate anyway. That's good. That's a good story. Anybody else observing? Dave or Doug?
I believe moved Jupiter and so the red spot project.
That's always cool to see. It's almost as cool as seeing the rings of Saturn.
We looked at that.
There you go. Vicki?
And I went to the Adirondack last weekend and, got to share my binoculars with my girlfriends. And so they all got to see.
Oh, that's great. Look at the moon through binoculars. The detail is fantastic.
And it was so amazing, seeing clear, just as you imagine. Great.
Fantastic. Peter?
Mike, I just looked one up. You probably did this already. Here's a brand new one for 700.
All right, 712 for a new one. Okay.
Including the tripod.
With the tripod. Anybody online want to share an observing story? I went to the Blackfriars Star Party. I didn't actually go to the official star party because I had a wedding to go to Friday night, and that's the first night of the actual star party. But if you, yeah, it's poor Quillen on my friends. Anyway, if you're into going to a dark sky site to see deep sky objects, you really are in for a treat because you get much better vision with very dark skies. And so there were guys there from Sunday to Sunday for that party. I went down Wednesday looking at the weather forecast. It was going to be very nice. I figured I'll stay Wednesday, and if Thursday looks good, I'll stay Thursday, and I can come home and go to the wedding, which was great. The wedding was great, but I did get some observing in on Wednesday and Thursday at Cherry Springs State Park down in Pennsylvania, and it was very, very dewy. Everything was soaked. There was so much dew. I could not keep the dew off of everything all night long. There was so much dew. I literally didn't cover my telescope knowing, because it was all wet. If I covered it, all I'm doing is holding all the moisture in. So Friday morning, when I woke up, and I actually ground camped, everything was frozen. So it got pretty cold down there on Thursday night into Friday morning. But I did get to see a lot of stuff. I started my Herschel 400 tour, got about 50 objects in the Herschel tour over the 2 nights. So that was fun to do. So they're really fun. And there's some really interesting things in the Herschel 400. One of the most interesting was Miroc's ghost. So Miroc is a very bright star in Andromeda, and it has a planetary nebula right next to it. And it looks like a ghost of the star that it's sitting next to. It's a very cool thing to see. So I highly recommend that if you can do some observing this winter. All right, anybody else? All right, we'll move on. Yes, Craig.
Question about you. I've been using my scope recently after having sat on it for years, being too intimidated to try it out. But I was affected by you too. I've been reading about like warmers that you can put on. I've got a new shield.
Yes.
But it's a passive thing, and that wasn't.
Yeah.
What do people do for that?
So dew heaters do work. What they'll do is they'll make your optics or the end of your scope warmer than the rest of the atmosphere around it. And so what will happen is you can prevent the dew from forming on there. But if you have so much dew around it, it'll just drip right onto it anyway. And that's what happened to me. I had pretty good dew stuff happening, but once you turn it off, you can't get it back.
Another option you could bring a hair dryer.
That does work.
I read about that.
It works. I have.
That works fantastic.
There's a guy,
Hair dryer.
mentioned that, the use of little, the former president, Joe Smith, mentioned he has a little ring, you put it inside the,
The optical.
NCT, whatever, you put that in, and plug it in, it works well.
Inside the ring.
Check the temperature you want,
That's interesting.
being
Put-
low.
Put a heater
medium,
inside
high.
the Schmidt-Cassegrain telescope.
That works great.
Cool. All right.
I regret it, I sold that, I don't know. who has it now.
All right. Okay. So let me, we had a couple recent events. We had a fall festival in Ionia, and welcome Natalie from our fall festival. We saw a bunch of people there. And I want to thank everybody who helped out. There's a lot of people that were there. So Dave Bishop was there, Lori was there, Vicky was there, I was there. There's a whole bunch of people. If I forgot your name and you're present, please tell me. But we had a bunch of people there. We must have had 60 to 80 people run up to the site. There's a hayride, so you don't have to walk up there. The hayride with the tractor, one of the tractors in the tractor parade, pulls you up to our site. And then Dave, mostly Dave, gave tours of the site all afternoon. Roger was there too. Roger and Bob McGovern was there as well. But it was actually a really nice day. In fact, you couldn't ask for a nicer day. And we were actually followed that up with about 7 new memberships. Probably Natalie was one of those people that joined us based on the feedback we got from the fall festival. So thank you and welcome. So a great event for us. Well, so I have a bunch of pictures. Here's our tent. We were getting set up. As the thing was going in the background, you can see all the tractors that were in the parade. There were 137 tractors. 127 tractors in the parade this year.
We can't see the screen from here.
You can't see the screen? It may be because I'm moving pictures in there. I don't think it comes through well.
I can only see you.
You can't see my presentation? Is that everybody? You not see the presentation?
Oh, yeah, you might have
Hang
to,
on. How's that? Do you see it now?
That's okay.
Yes, that's good.
Yeah, I see it now too.
Oh, that's great, but now I can't move it. Okay, there we go. And then there's some of the tractors in the parade. It was a pretty good day. Here's the hayride that went up and back and forth to the site all afternoon. So if you haven't been, I highly recommend. It's a lot of fun. Here's some people walking through our site on Saturday afternoon. You can see it was a beautiful day to take a tour of the site. And during the day, you get to see all the observatories and what we're doing up there with the different observatories. All right, so we also had another recent event, a unique event. We had a Heroes Brewing approach us with an opportunity to make a little money and also a little publicity by releasing a New England IPA, milkshake IPA called Nebula. This is their first can that's actually black. All their other cans are white, so it doesn't work with our business. We like nice black sky. So they actually made a black can with a heart nebula on it and released that on September 22nd. Greg Fagan is the president over at Heroes Brewery. He asked me, what's a good day to do it? Is there an auspicious day coming up in September to do that? I'm like, well, the only thing I could think of is we've got the autumnal equinox on the 22nd. He says that'll work. So that's why we chose Wednesday, the 22nd as our release day. And a number of us were there for that event. We probably had almost a dozen people there. We didn't get pictures of everybody, but it was a fun event. I believe there's still some available. If you want to try the Nebula IPA, it's not cheap. It's like 18 bucks a 12 pack, and then plus tax and deposit. So it's almost 20 bucks for a 4 pack. So it's fairly expensive, but it's very good. That was a fun event, and we'll make 25 cents a can on that when it's all said and done, which isn't a lot. We'll probably get 80, 90 bucks out of it, but we'll also have our website on the can, and a lot of people interested, an opportunity to see what we do and maybe get interested in what we're doing. Okay, upcoming events. We have member observing tomorrow, although tonight might be a better night to go up there. It doesn't look really good tomorrow night, but we'll have member observing tomorrow night. And we also have an open house during the day from 12 to 4 p.m. So if you want to see the site and learn how to use some of the equipment up there, come during the day tomorrow. We have our board meeting next week. We're going to be meeting, we're back at U of R, but we'll also do this remotely with Zoom. If you want to join us for our board meeting, that's Wednesday. Let me know if you want to join us. Any member can be part of our board meeting. So let me know if you want to join, just email me and I'll send you an invitation to join the board meeting with us on Wednesday. And that's at 7 o'clock. We try to keep that to 2 hours, 7 to 9 p.m. next Wednesday at the U of R at the Bausch and Lomb building. Next month, we have our speaker will be Segev Bezdi. He's also from the University of Rochester. He's really into dark energy, and he'll tell us a little bit about the new dark energy spectroscopic instrument on Friday, November 5th. And then preceding that, we'll have our elections for board officers for the astronomy section for next year. Speaking of which, here is the slate of candidates. Looks a little different than it did a year ago. We have some new people on board. Always glad to have more people joining us. So I'm running again as president for next year. Dave Bishop will run as vice president. Vicki Rotolo is running for secretary. Eric Day, if you're familiar with Eric Day, will be taking over as secretary from Bob Easterly. And Bob is actually working with treasurer, excuse me. Did I say secretary? I'm sorry. I meant treasurer. Bob Easterly will be is actually working with Eric now to transfer those duties over to Eric, who will begin as treasurer in January. And then we lost the microphone. I don't know what I did, if anything. How's that? Don't know what I did. Nothing.
How about trying another microphone?
Did I lean on something? I wonder if I leaned on something here.
Looks okay here. You could try using this. If you
Does this work?
oh, here, let me try it.
Test.
No. It's something in the wiring.
Okay.
Sorry, nothing we can do about it.
I will talk louder. Okay, and then our directors will be Bill Rogers, who is continuing as director. Tony will also be continuing as director. And then Bill Schlein will join us. He was a member of the board years back, and Bill Schlein will be joining us as a director as well in 2022. So welcome, Bill, aboard. And I want to thank Bob Easterly, as I've thanked in the past. Thanks. There, now it's back.
It's getting feedback. It's my fault.
Okay. I'm not going to touch anything. We'll thank Bob Easterly for his service as treasurer over these years, and Mark Dudley will be stepping off the board for a while as well. So thanks to Mark for his work as a director over the last few years. And all this will be on the slate for us in November when we vote for our new board of directors. Very communist board. There's nobody running against each other. So we build a slate, and you'll have the opportunity to write somebody in if you don't feel somebody here is qualified. Yes? Okay. And then in November, we'll also have an open house on the 6th, Saturday the 6th. And member observing as well the same day, since it also works out to be the new moon weekend, we'll do that as well on the same day in November 6th in Ionia. And our board meeting in November is on Wednesday the 10th, same place. We'll also offer remote for that as well. I'll leave the Ferris Center protocols are the same. I do want to present them every meeting so you can see what they are. Really what it amounts to is we're still under the auspices of COVID. So if you're bringing people that are not members, we need to know who these people are, especially if they're at the site and we end up with somebody with COVID. You do need to have we do need to have contact tracing. We're required to do that. Masking indoors is strongly encouraged, and if you're less than 6 feet apart and you're unvaccinated, we definitely need you to be wearing a mask while at the Ferris Center. Bathrooms are available for use. We will be winterizing a bathroom shortly upstairs, and then the downstairs bathroom is actually a warm room during the winter time, so that's always available. Questions on this? You had a question, Ken?
Yeah, I'm making a suggestion, if secretary or something would take a sheet and get the name of the people who showed a proof of your vaccination card. You already had the booster, just saying. Proof that you already had the shot.
You can still catch COVID, Ken, even if you've had the shots. So we just want to know who's there. Yeah, we're not tracking who's been vaccinated. We're just tracking who's been together if we have a case.
Well, I'm just saying for everybody's behalf, for their own safety, that's all.
Appreciate that, Ken. Thank you.
Just trying to help.
Is Tony here? Or Tony, are you online? Let's see. Give me a second here. See if I can get I don't see Tony here. It doesn't look like he's here, but he still has shirts left. I don't think he's distributed all the ASRAS wear, and it's pretty cool stuff. We only got a little bit extra. That was really for if we needed to for giveaways. So we're gonna hang on to those, but we could make another order next year. But if you've placed an order, we'd like to get your order to you. So if you haven't picked it up yet, I'm sure you see Tony. Anybody waiting on their order yet? And he's not here tonight.
He said he'd be here.
He did. Oh, maybe he's running late. Okay. Okay. All right. I think. Oh, we got a couple more things. So Blackfriars Theatre has I mentioned to you a couple times now. Silent Sky, which is about Henrietta Leavitt, is on. You want to say a few words, Jackie?
Sure. Hi, for those of you who know me, I'm Jackie Amagon. For those of you who don't know me, I am Jackie Amagon. And in my other life, I work with Blackfriars Theatre. So Silent Sky, like Mark said, is about of it. It is a fictional play. It does follow her life. And partnered with for production. I have Mark tonight. I will be giving you an envelope with 2 complimentary tickets for the show, so you can use it as you wish. We've also worked out an arrangement for discount tickets. I can't remember which day that was.
It was November 13th. That's Saturday at 2 p.m.
Okay, so there are discount tickets. Mark will be able to give you all the information on that. We also, and Mark, I will tell you a break, on October 31st, which is the Sunday matinee, we call the Sunday Salon, but it's a talk back session for audience members, and I'll be talking to you about that. So if anyone wants to come, ASRAS for partnering and looking forward to, doing more community outreach. It's going to be a fantastic show, and we had a production meeting this week, and sort of looking at some of the lighting effects, and we're going to be turning the theater into the sky.
That's cool.
So it's going to be really, really cool.
Looking forward to that. Thanks, Jackie. Great partnership with Blackfriars. Looking forward to seeing this show. So as Jackie said, maybe you guys online didn't hear all that. We're going to have an ASRAS event where we have reserved 30 seats for the matinee show on Saturday, November 13th. Those are discounted 15%. If you call the office, tell them you're from ASRAS, the astronomy section, and you get a discounted ticket from them then. You can actually get a discounted ticket for any show you go to, but as Jackie said, there's also a salon show on October 31st. I actually thought about doing that one, but that's Halloween. I didn't know how popular that would be for people to go to that show. But if you're interested in that show, that's the salon where the cast comes out and they'll answer questions from the audience. It's kind of a cool thing to see when you have a production, have the cast come out and talk. It's a lot of fun. Questions on Silent Sky? Awesome.
It is not
So-
a documentary, it is a fictional play, but it is based on her life and it follows her research.
And you'll get to know who Henrietta Leavitt was. She was pretty important in astronomy. Lastly, membership renewal. It's that time. We're getting towards the end of the year, and this is when we start to appeal to you to renew your membership. If you've become a new member within the last few months, you certainly do not need to renew your membership. Your membership will carry you through 2022 if you joined us after July 1st. So welcome for the duration of 2022. But existing members, it's time to renew. This has been in this renewal form was in our newsletter. It'll be there again the next couple of months. And our membership chair is in the building right here. Craig in the orange shirt with the beautiful white ASRAS logo on the front will help you renew right here today if you want to see Craig to renew. He's got forms and he'll take checks. So that's the best of all worlds. So if you're here tonight, you can renew with Craig. Right. I believe that's it for my announcements. Doug.
You were mentioning the council events.
Yes.
We also have
Hang on a second. The noise in the background. You're having a paper session that day. Oh, that's right. The RIS has a paper session the same day. And that should be on this list of stuff, and I didn't put it on there. So where is the paper session and what's the timing on it, Doug?
I forgot the exact time that it's starting. There's a lunch. Speaker.
Yeah, so also on November 6th, look at the Rochester Academy of Science page. There is a paper session. I'm remiss in not having it in my announcements tonight. Yeah, those are pretty cool to see some of those displays that they put up. That's really an interesting event. And the talk sounds interesting on corals if you're into it, especially for the mineralogists and the fossil people. Anything else? All right, because we're spread out, we got people in here, we got people online. We'll take a break only as long as it takes to get Alice set up here. And what she's going to do is log in, and we'll make her share her screen versus trying to get everything going on my computer. So take a break if you will, but we'll bring Alice on and I'll get your attention. And Tony has arrived. If you are here and you need your shirts. All right. Give us a minute here. We'll get you right back into the swing of things. So we get you plugged in over here.
Your battery just.
I'm just going to move mine over here.
Just come on back and
Hang on a second.
Oh, it goes great. I don't even need my adapter.
No. Oh, that's just your power.
Oh, that's power.
So you-
Okay, now I need this too. I need to,
So what we'll do,
oh, we're gonna share screen? I can.
yeah,
just
so
put
what
it
you're
on
gonna do is
the
you're gonna,
So you need to stop sharing then. Thank you.
yeah, so I'm gonna stop sharing.
sharing.
Next week.
There's my Zoom control, there's my meeting controls. I'm gonna stop sharing.
There we go. Now I can share. Most disabled screen sharing.
Okay, let me see if I can make that happen. Multiple participants can share. Okay, you should be able to share now.
Oh, there it is. Find my thought.
We have to check out.
Here it is. Share.
You've been to the
That's
site.
you.
Yeah, that is.
Yeah, but
we're not there.
Where we might be.
There you go. Awesome. Oh.
Yeah, I think I've been there once.
Give me a second here. Give me a second here.
Oh, we just have to. There we go. In my talk. Yeah, okay.
Okay, that's you.
Yeah, that's
I
me.
believe this mic is working.
Kind of working, yeah. Yeah, it's kind of.
Okay.
Try not to lose
Give everybody the. Yes.
She's got a she crocheted covers around I don't know how she knows about that. I don't have a problem. It's just they need to know. They don't want to be responsible for it. So if it gets wet, whatever, you don't want to be responsible. I only have a count on bag. Where would you propose leaving? She just solar That's a really small roll. Okay, how about the big dump? That's fair. That's not a bad idea. She's got a perfect arrangement of
I can't make a unilateral decision because that's their program. So that's their role. They're not gonna be responsible for it.
I can't.
I understand. That's why you gotta get smaller stuff. I'm just teasing you.
Never have it back.
We'll get everybody back together. All right, if I can have your attention, please. We'll get back together here. We're all loaded up, ready to go. Give Alice all her time that she needs to do her talk.
You need to remind me how long I'm supposed to.
We don't break up till 9:30.
Oh, okay,
Lots of time.
really, it's up to you guys.
So,
I can talk forever, but.
so
But,
you're talking and your questions.
Okay. Oh, really?
Go ahead.
That's fine, that's fine. Okay, you guys.
All right, if I can have your attention, please. Everybody take their seat.
She is a freshman here, and she has a younger brother who's 2 years.
You always use the lights.
Ah, very
You
good.
can say, you can do that, and then
They live down.
lights go down, everyone's like, oh, she's gonna start talking.
Oh, really? Yeah, dark. I guess we could turn it back up. It does work to get people's attention. though.
It does. All right, without further ado, let me introduce Professor Alice Quillen from the University of Rochester. Thanks, Alice.
So I'm going to tell you about soft astronomy. What's soft astronomy? So soft astronomy is things that can deform. Actually, so this is a picture of Bennu from OSIRIS-REx. And, you know, you look at these new pictures, this isn't that old. If they're just really inspiring, you're trying to understand what's going on. There's this little weird rock there perched on the surface. How do you get a rock perched on the surface? And what happens if you hit it? What does it do? So then this other thing, we kind of got into this, like how do astronomical bodies behave as solids, you know, because I started doing spin dynamics with the spring models. So these are just a bunch of masses and springs, not very complicated physics. But it can get really complicated when you think about the evolution and the dynamics. So that, in this particular simulation there, it's a binary asteroid. And many of the near-Earth crossing asteroids are binaries, actually about a sixth of them. So, this one is in your crossing asteroid, so potentially hazardous, right? But also we can get close to it easily, not necessarily too far away. It has this kind of funny top shape. So what happens is they spin up, and sometimes when they spin up, sometimes material fluffs off the equator. That's maybe why it has that funny. But sometimes that stuff can actually fly off and form another body, and that's maybe how the secondaries form. And then once they're like that, how do they stay without falling apart? And so that's one of the stories I'll try and tell you about. But I'm going to first talk about unusual direction that we went into, and that's the laboratory aspects of it. So here's a couple more. So that's the same image here. This one's Ryugu. There's a Hayabusa 2 mission, Japanese mission went to this one. And it's not exactly the same. Actually, you can tell the difference between them, because this one is much grayer. There's a much less difference in the reflectivity and the absorption of the rocks. Whereas here, there's kind of dark rocks and light rocks. So if you stare at it, you get the impression that there's light and dark here, but not on that one. So there are compositional differences in those two, even though they both have these top shapes. So that top one is Itakawa. And Itakawa was Hayabusa 1 Japanese mission. And it has smooth regions and rough regions. So there's various speculation. How do you get the rough regions, and how do you get rocks to be on top of other rocks in that one? So So why are these systems really complicated? Well, so it's a granular system. You think a bucket of gravel, but maybe it's got big things underneath. Maybe it has ice underneath. So you don't really know what's underneath. Well, granular systems are confusing, even on Earth. So they can flow kind of like a fluid, but they can act like a solid too. So you can actually, if you throw a stone, it'll skip off the sand. So, and that, I mean, I guess you can do that in a fluid too with water. But how do you know when it acts like when something bounces? How do you know when you don't sink in? And so it can also act like a gas when, you know, if you have a ejecta curtain, for example, and things are colliding. So how do you predict what it's going to do? And so there's this whole field of granular physics that tries to understand granular flows. It's very nonlinear. There are many regimes for how it behaves. And to make things worse in space, we don't really know what it's made out of. We don't know what happens when you have microgravity. We don't know if air is important in its behavior. So like all of that adds up to people not knowing how these things are going to behave. So there's some real reasons we care. One of them is that they are potentially hazardous. So you might want to be able to push it out of the way. And if you don't know how it's going to respond, it makes it really hard to make a successful plan for that. From a scientific viewpoint, maybe you want to send a mission to make a sample collection and land on it, take something. But if you don't know how it's going to, whether it's going to bounce or sink in, that makes it hard to make that mission succeed. And then when we look at those pictures, how do we understand what happened to them? So do we understand the evolution and the formation of them? Do we understand what causes the flows? So even just from an intellectual curiosity viewpoint, it makes you want to like study the granular systems with this view. So I was looking at these pictures. It's not just doing experiments on granular systems for their own sake. It's like, how do I learn how to scale it? So if I do an experiment in the lab, that I can make a prediction for how something in space will behave. So it's a little bit of a different, you know, space to intellectually when you're thinking about lab experiments. So so I mentioned you know, potentially hazardous. So in the next month there's another mission called DART, which is the double asteroid redirection test. On board there's going to be an Italian little imager, but the main thing that happens is it's going to slam into one the secondary of a binary asteroid, and the secondary is dimorphous, the primary is called didymos. And then the idea is to look at it and see what had happened to the secondary. So this is a real impact. It's a hypervelocity impact, so a few kilometers a second, and see what happens. So how much momentum transfer, what happens to the pulse, what happens to the spin, all those things that might be interesting. So I'm kind of interested. So when will this happen? The launch is in about a month. But the impact itself should happen about a year later, so a year from November. So there's lots of reasons I'm interested in this this mission. One is we have a prediction.
Fuck, I missed that.
And the other is that we're trying to understand how pulses propagate through granular materials. And so we'd like to have some prediction for how the impact pulse changes the asteroid. But we don't yet. So I kind of mentioned this, how do we interpret surface materials? And how do we predict what happens to landers so that they actually succeed in their mission? One thing that we noticed in this field is there's a lot of studies on impacts, like people go into the lab and they fire things at high speed, like kilometers a second into something, and look at the crater, how the crater forms, and you can study crater formation. So why high velocity? Well, the reason high velocity is if you look at the velocity differences, things in the asteroid belt or things, you know, interstellar speeds, they tend to be very fast, like many kilometers a second. But if we're thinking about an asteroid that might speed up and material comes off of it, that material is going to come back and it will hit the surface slowly. And so the low velocity regime has kind of been ignored because people didn't think it was important. But now we're kind of realizing it's important. It's also important for a lander because probably you're not going to send a lander and high velocity. You want it to touch down and not annihilate itself. So the low velocity regime is interesting for a number of reasons. And then this other issue, can we predict what DART is going to see next year? So yeah. So following an impact, what happens and what kinds of particles would be ejected? What's the likelihood of something bouncing or sinking in? How treacherous is the surface, in other words? So a bunch of other mysteries. So one of the reasons we started this whole thing is we were in the lab and we were playing around with these granular materials, and we got to a big argument. The guy got into an argument with Professor Nelson, who passed away unfortunately last year. But he was so important to this project. And one of the reasons he was important is because of this argument. And he just said, things don't bounce off of sand. And that's wrong. But almost every argument I ever had with Randall, I lost. So when you get one that you think you're right and he thinks you're wrong, and I thought I was right. Well, I could show him I was right by throwing a stone onto the sand and watching it skip. But if we had an argument, it wound up, then it made it an interesting project. You know, if there was no agreement, it means people didn't know the answer. And almost in every other setting, he was right, and I would, you know, cave eventually. So in this particular case, he wasn't. So there are other reasons. So this is a particular two views, two pictures for impact on asteroids. They're actually inconsistent, probably inconsistent. So if you have an impact on an asteroid, it might generate a seismic pulse. So if you have seismic pulses are used on Earth to like look what's underneath, and people feel earthquakes. So you know from explosions and stuff like that. So impacts cause pulses. What happens to those pulses? So there are two arguments. One is that it's a big jolt and it decays really rapidly. And the reason why people think that would be true is because granular systems are expected to be dissipative. You know, you don't really expect them to act like an elastic material. So a seismic wave is an elastic wave, right? So why should it travel very well? On the other viewpoint, there's seismic reverberation model, where the idea is, well, there's nowhere for the energy to go. You know, it's small and there's no air. So there's no fluids, no water, no places for it to dissipate. And to support that view is the measurements of seismic waves on the moon, where they actually traveled really far without damping. The damping rate was much lower than on the Earth. And this was attributed to the moon being really dry. So, and on the plus side for the seismic reverberation model were those pictures of boulders perched on the sides of those asteroids. And people were saying, well, if an asteroid starts shaking, you could get what's called the Brazil nut effect, where you have these big boulders that kind of float to the surface. So, so this was, the reverberation is like thought to be a requirement to explain why there are these perched. And on the opposite viewpoint is a particular study of craters on Eros, where they argue that there's one crater on one side that causes littler craters to be erased or degraded, I guess, where they get smoothed. I think I have a picture of that. Well, so before I get to the crater erosion model. So going into our lab, so what are we doing in the lab? Well, so we were looking through the literature on impacts, low velocity regime impacts. We noticed that almost all the experiments were done with normal impacts. And the last, actually only experiment that we could find published on ricochets was like done in the 70s. So it was like, great. We were thinking nobody's looked at ricochets in sand for a long time. And the only one paper didn't really think about it very carefully. So at that point we were like, we got to drop everything and work on this. Because we know things bounce, they don't always bounce. But when do they bounce? Off of sand. So so here's our little experimental setup. It's basically a pendulum It's got this little turkey baster thing that's like gives you a little vacuum. You put a marble in, you bring back, you squeeze the air out, it holds onto the marble, and then the pendulum comes down. And you set the height, so it depends. The impact velocity will depend on the height that you drop the pendulum. The pendulum drops. It hits the stop bar, and where you put the stop bar determines the angle that the little marble is launched. And then there's this sand thing. You can see over there, that's actually a picture that it bounced and then it ricocheted and bounced again and then rolled. And the surface there was flattened. And then we shine a lot of lights on it because we film it with a high-speed camera. And we also, we got good at tracking our marble. So we painted it, the white light actually gives you one dot that's really bright. So that's a good way to track the center of mass. But we also painted it with little dots that fluoresce. And so the blue LEDs will give you these fluorescent dots that are different color, they're green for us. And that lets us track the spin of the marble too. So we can actually see the spin. So here's some of the high-speed camera videos. And the top one, you can see that's our marble, and you get this nice ejecta curtain. And you'll see a second ejecta curtain on the top one. There's the second ejecta curtain, and that's the one that's bouncing. So when it actually, and then this one rolled, you can kind of see it rolling. This one, it just stopped in its impact crater. So those are 1,000 frames per second video cameras. So one of the great things that happened in a couple of years is the price for high-speed cameras dropped a lot. So it became affordable if you didn't have a really big setup. But we didn't actually have any lab experience at that time, really. So so we got a hold of a high-speed camera. And now we did get funded, but only after we started doing these experiments. So, so these are the three types of phenomena we see. We're calling them a stop, a rollout, and a ricochet. And so I did a lot of experiments where by eye after the experiment. So I just raised the pendulum to different heights and moved the stop bar to change the angle. And then I would write down what happened. Did it roll out or did it stop? Did it ricochet? And so on the vertical line, you've got the impact angle. So low angle is nearly grazing, and high angle is nearly more perpendicular. And then in the horizontal axis is the impact velocity. And we're scaling it actually. So that's actually a dimensionless number. And why? So this is important. So we want to actually do these experiments on Earth, and we're going to be able to predict what happens in space. So the important parameter is the gravity. So so our little marble, which is a centimeter, it's moving at a few meters per second. On 1G should scale to like a boulder of a meter going at below the escape velocity, which is some few centimeters a second, in like 10 micro G, which would be like one of those asteroids I showed you. And so it all scales off of this dimensionless parameter called the Froude number. So we're predicting that the scaling works like that. We don't really know that it does, but crater scaling for the dimensions of craters works with mainly depends on this dimensionless number. So, you know, it's likely, so argue that it's likely to be an important parameter in the problem. So this kind of says that, and again, this is, you know, why am I working with this dimensionless number? And that's because we want to relate it to stuff that's going on in space. So this shows you a little bit about our tracking. So the white light, see the white light right there, that's the white light dot, that's letting us track the center of mass. And that's that red line. And then we measure where the white light dot is at different times. And then the top image there, I'm showing you what happens to the little green dots. And they actually do arcs as the marble spins. And so we can actually tell how fast it's spinning as it starts to touch the sand. So here's all the different ways people try and understand granular material. So there's a series of papers where people did normal impact experiments. Some of them were done in drop towers where they mimic low gravity by doing the experiment while it's falling, but not falling. It's like with the pulley system, so it's not falling as fast as it would be with, so if it falls completely, there's no G, so you let it fall really slowly as if it has a little bit of gravity. And what they find is that you can model the normal impact, like the interactions with the granular media, with like a drag-like force and with a hydrostatic force. So the hydrostatic force pushes up. The drag force also pushes up but it scales with velocity squared. For the grazing impacts, this actually has to bounce up. So something has to push it up. So we're guessing that it's going to be like a lift force that'll go as velocity squared. So these are really simple, we'll call them empirical models, and they've been used in a whole bunch of experiments in draft towers, only normal impacts. So our system is a little bit more complicated. We've got 2 dimensions, not just one. The horizontal component. We have to have drag coefficients in the horizontal direction too. So what do people do in granular systems? So most, so this is actually an interesting story. So this GDR-MIDI-04 is a French consortium since 2004 over across the whole country in France. They got everybody together who worked on granular systems, and they had a big conference, and they tried to come up with a single story about all of their experiments. And so many experiments were put on similar plots by scaling arguments. And there were, they identified a bunch of classic experiments like granular systems rolling down planes, funnel flow, things in drums. So there's like a bunch of classic examples. And they said, we're all going to standardize by understanding these experiments. And they also set up a system where numerical simulations people should be able to match what they see experimentally. So it's a great example of community-wide approach to understanding complicated problems. And so the people, there's no author list on this. It's just cited as GDR-MIDI. And I think it took place in some, someplace in the Pyrenees or something called MIDI. But yeah, it's a really interesting paper to read. Well, so one of the things they used is this dimensionless parameter. That's the ratio of shear rate to shear stress. It also has the grain diameter in it. It's actually really hard to figure out when you've got a flow what this dimensionless number is doing. But there are a bunch of popular continuum models that try and use that to come up with predictive simulations describing the flow. I find these very hard to use because I probably have to have a whole simulation in order to compare to my experimental results. So more accessible might be this this other class of theories called resistive force theory, which is used by people working in robotics. And what they did is they gave up on the theory and they just started pushing plates through granular media, and they pushed them at different angles and with different, if you have it at an angle, you can push it at, you can set the plate at an angle, you can push it in all different directions, and they would just measure how hard it was. And so they tried to come up with a picture. So if you have a surface, you could add up all the forces from the different pieces of the surface. And that is only, so that theory, which works well in robotics, has only worked for low velocity regimes. So it's not inertial. And when I say inertial, when we're looking at lift and drag, we have forces that depend on velocity squared. So far, the resistive force theory hasn't been expanded to take into account the velocity dependence. So like this view graph is just kind of giving you my summary of the field. But the only thing that we managed to get to compare to our data are these empirical models. I just, the other parts seem more complicated. So I made a model where we have empirical force laws explaining the penetration phase that were consistent with the normal impacts. And then I adjusted all the parameters to give a rebound phase with the had a lift coefficient. And that model gives you a maximum height in the rebound phase. And if that height is above the surface, you say ricochet. And if it stays below, then it's a stop. And if it's just near enough the surface that the center of mass is above the surface, it can roll. And so it does give you a roll. The criteria for saying the model gives you a roll. And so that's what these lines are. Those are predictions from this very rough empirical model. The nice thing is once you've got lines, you can then go say, well, what if you believe my scaling? Then what would we predict for an asteroid like Bennu? And so that's what this picture shows you. So it's projectile diameter on the left and the asteroid diameter on the right. And the red lines tell you whether something that would ricochet if it's at the escape velocity, and the blue lines tell you what if whether it would ricochet at 0.1 of the escape velocity. But it's basically, so the y-axis is in meters, so it's telling you that boulders will ricochet. So we're predicting that most things that come in at grazing angles that are large would ricochet on asteroids. So meanwhile, so we're actually the only people working on ricochets at asteroids, but meanwhile, 2 years ago, the ASRAS team noticed that there were particles escaping from Bennu, and one of those particles actually came back and bounced. And this is a centimeter particle. So smaller particles bounce too. And then the mascot lander on the Hayabusa 2 mission, which actually touched the surface, also bounced. And they, prior to it getting there, so the mascot lander is this funny thing. It has this big arm, and it was supposed to touch the surface and then swing the arm, and that was supposed to help it. But it bounced before that even happened. So things bounce on asteroids, but nobody knew that whether they were going to or not. And so this is a big concern for the success of the sample return part of the Hayabusa 2. But anyway, so small particles bounce, ricochet too. So how do we fit that into our picture? Because so far we've only said that big things bounce on asteroids. So so we decided to do more complicated experiments. So one of the things, so in the normal impact regime, people would just do experiments on whatever they happen to have around. And so there are various materials. People are dropping projectiles into like glass beads. Why people really like glass beads? Because they are spheres. And so, you know, there's all this physics done with bouncing glass beads, but they also know the elastic modulus. But some of the experiments did things like sand and more amorphous things. On asteroids, in space, the densities of things don't tend to be very different. Like, you know, the difference between ice is 1 and rock might be 3 grams per cc. So, whereas on Earth, people like for some reason want to drop steel balls into glass. You know, so there's always this big density difference. So most of the experiments previously had looked at the role of density ratio and impact velocity. So they weren't looking at angle, but so we decided what we should do. We were curious about the size. So here we've got coarse gravel, which is one day where we get all this gravel. One day Randall showed up in the lab with like a whole driveway full of buckets of gravel, and that was like a stealth mission because we showed up and it was like, what? In any case, Randall's driveway gravel. And then fine sand, playground sand. And then I went to Lake Ontario and wandered around enough until I could find a coarser sand. We really needed something in the middle. So the coarse sand is actually Lake Ontario sand. And then we tried to make experiments where everything is the same except the size of the granular material, the grains. So we're matching porosity, density, the projectile is the same, the angle, the velocity, everything. And actually, one of the things you can do with the granular material is you can, make a cone shape. It's called the angle of repose. So if you pile sand on top, it will slide down. So we measure the angle of repose. It's related to the friction between the grains. They all have about the same angle of repose too. And we did a lot of sifting. So this is where, the poor grad students spending hours at various sieves. And that's Esteban. I did a lot of sifting too, actually, and a blow dryer too, because when we get the sand, often it's wet, so we have to dry it up. So each medium has a narrow range of sizes in it from the system. And so the key parameter now we're varying is grain size to projectile, or projectile size to grain size ratio. And so what do we see? Yeah, so actually you can see what we see. So we're going from, the nice way to think about this is we're going from a ballistic setting. So you have two rocks hitting each other to a setting where you have a boulder hitting a smooth continuum thing. So here you have these really smooth craters, fine sand, but at the top, the coarse gravel, you can see it didn't make, it actually bounced further, and the crater is not as deep. So, so there's actually quite a difference. And then everything in between, you can, for some reason, that one in the middle bounced closer than the finer gravel, but you can kind of see the craters are less deep and there's more higher, they bounce more higher off of the coarser material. So this kind of shows you a lot of experiments where we're tracking. Probably the most interesting thing is the top panel, which is showing you, yeah, so when it ricochets into sand, it doesn't deflect. But when it ricochets in the coarser material, it does deflect. And so that top panel shows you the direction of deflection. So it's like we're looking above and we're measuring this direction for the trajectories. So, and this is a setting where actually to try and predict what's the distribution of deflection angles. So if it's in the fine sand, it doesn't deflect, and there's a very small distribution of deflection angles. But in the coarse ones, you get a distribution that's much wider. So what we're plotting there is the standard deviation in the angle. So it's the angles are scattered. And the 3/2 power fit it, which we managed to match with like a collision-based model. So the idea is you try and figure out how many grain collisions do you need to stop it. So you have to turn it upside down you have to make the velocity flip to make it bounce. But during that time, you have random collisions in the opposite, in this direction. And so you add up statistically, what could they do? And that can give you these deflections. So if it's not very many collisions, then you have a higher probability that it won't be balanced and it will come out at an angle. So that's what that line is. But that's actually a collision-based model. It's not a fluid model. So this is where you get, this is where these different viewpoints for how you think about granular media come in. Do you think about it as if it's a gas, or is it a solid, or is it a fluid? In different settings, you get different answers, or different ways to make estimates match what you see in the lab. So we saw higher bounces on the coarser media. So what can we measure from that? So what we did is we measured pre and post bounce velocity. That's like a coefficient, what's called a coefficient of restitution. You think about a rubber ball, how if you let it fall, does it bounce all the way back up? Well, it won't bounce all the way back up, but it bounces pretty nearly all the way back up. So the ratio of pre and post bounce velocity is this coefficient of restitution. So if a rubber ball would have a coefficient of restitution nearly 1, but a marble on a hard surface would have a coefficient of restitution of like 1/2. It wouldn't go all the way back up. It does bounce them. So, but you can measure coefficients of restitution for the vertical component and the horizontal component. So the pre and post velocity horizontally could also be different. And that's because while it's interacting with the granular media, there's like a drag force on it. And so it is slowing down in the horizontal direction too, but less so in the coarser media than in the finer media. So that's what we measured. And so we got things that look like this. And then we came up with a model that was based on drag coefficients. So what do the drag coefficients predict for the coefficients of restitution? And that's what this plot shows you. So here we have, again, we're thinking more ballistic, more like a continuum. And so the idea is, if you have a small pebble and it hits something that's about its same size, you would be in the more ballistic regime and it would be more likely to bounce. So that's the way to maybe make sense of why did the pebble, the little centimeter thing, bounce off of the and it maybe helps explain why the mascot lander, although mascot lander is about 1 meter big, so it's maybe not too far off from what we were predicting in the first place as being likely to bounce. Okay, so that kind of tells you the takeaway from this is things bounce off of sand, but things probably bounce off of asteroids too, particularly if they come in the day. So now I'm going to get back to this other story, high attenuation seismic jolt versus low attenuation ringing picture. So whenever you see, like in the literature, you have two competing views that are kind of inconsistent, that means it's like a place to go and try and see if you can make sense out of it. So so again, the little boulders on top are the supposed to be because the whole asteroid's been shaken, and on ASRAS, it's got this really big crater on one side, which I think is the top. So let's see. Yeah, here's the picture. So this is the seismic jolt model was proposed by this particular collaboration studying ASRAS. And what they did in the middle here is they plotted crater density. So they counted all the craters on the surface, and they found that there were regions that had fewer craters. And they tried to explain the regions with fewer craters by saying that this big impact that made this big crater, I think it's the Shoemaker crater, actually made a big enough jolt that it erased the craters. But the idea is it only erased the craters near the impact point. So that, proposed for ASRAS. And on the opposite side, the Brazil net effect is supposed to explain the boulders on the surfaces of asteroid Itokawa. So I don't know if the last time I was here, I think I had started working on these mass spring models. But one of the things that started me off on this project is I was curious about how would elastic energy propagate through an asteroid. And so I used the spring model with one of the Bennu shape models to try and see what would happen with where the seismic energy could go if it was elastic. And so that's what this simulation shows. So, so if there were a reverberation phase, where would the energy pile up? And the thing you mostly see, I can kind of show this again. Let's see, start again. You can see there's the impact. And then it comes and it focuses on the side. So there's an antipodal focusing where the energy goes like this and focuses on the backside. And then there's points on the equator that get extra energy, so you can maybe cause some sliding of material. But when I was looking at this, there was no way to decide how fast should that pulse energy go away. And so this was one of the reasons we were motivated to go in the lab and start looking not just at ricochets, but at pulse propagation. So, so here's another, so why would we think maybe that pulses would go through? So this is, Newton's cradle, but put up on the side. And that is a simulation of a bunch of soft spheres by Pretty. And you can see the pulse go through. And then you can see material comes flying off. So a pulse that's hit on one area can propagate through and then cause material to launch off the surface. And that's what you see with the Newton cradle. If you hit it on one side, all the balls bounce up against each other and the one on the top bounces off. So this may be potentially one way to get rid of seismic energy, is that you just launch material off the surface and then have it rain back down. So so we went into the lab. And this is actually a regular speed video. And what is it? It's a bucket of the same gravel, but in this case we mixed different particle sizes. And so the green ones, we painted all the big ones green. We painted all the little ones pink, which required a lot of time spray painting of gravel. And then this big bucket, you hit it with a sledgehammer underneath. And what happens? So this is a single pulse. I think I can play it again. Here it is, there. What happens, a single pulse puts all the big things on top. So it's not, it doesn't really require shaking. You can just whack it, all the big things will wind up on top. So why is that? So here's a high-speed camera picture, and everything looks like it's moving together. except that things land, and then things get complicated. So we did some tracking of particles, and so these are all the arrows of the particles. And they're all moving together except at the very end. And so what happens is that all the big ones are together with the little ones. It goes up and it comes down. Then when they start to land, the little ones just bounce off the big ones. So this is a process called ballistic sorting, where it's the collisions themselves that are giving you the big ones on top. So it's a little bit different than this shaking, where it's not really clear why the big ones, maybe the little ones get underneath, or why is it when you shake a bunch of nets, the big ones rise? This is a ballistic sorting technique to give big ones on the top. So you don't really need reverberation to explain why boulders are perched. So yeah, so this to summarize, our experiments show a single strong pulse that ejects gravel off the surface can leave previously buried boulders on top. And what we saw is the ejecta moves together, and then all the sorting happens at the landing, when things are landing and scattering off of each other. Okay, so that was a move on. So I was saying we're going to study pulse propagation. So these are our experiments that we're working on now. So I don't know the whole story of what's going on with this, but this is very enthusiastic student. So Juliana, who actually got a grant from the astronomy, them, to buy materials, including this millet here for this experiment, and Max, who built the accelerometer array. So he's a very clever. He's not a freshman anymore. He's a sophomore now, but. So it's an accelerometer array. That's 7 accelerometers. We have 2 oscilloscopes with 8 channels each. When the ball drops, it triggers all the oscilloscopes to start taking data, and we place all the accelerometers with these tweezers in the millet. And so we have this little tub, and we were worried, well, is the tub moving or is the waves bouncing off the side? So now we're working in big wash tubs. These are 11-gallon wash tubs, which you can actually mail order. So we have a whole bunch of wash tubs. So why millet? Millet, it's actually nice. The reason it's nice is the pulses decay really quickly, and so it fits in our container. Otherwise, you're worried you're going to bounce off the edges and see something else. So, so this is the current experiment. So oddly, there's lots of experiments looking at pulse propagation in granular materials. None of them use accelerometer arrays, so it's not very expensive experiment. Accelerometers don't cost very much, but you do need a decent multi-channel oscilloscope to actually take the data. So here's some of our pulses, fresh off the labs. I think we took this data on Friday, last Friday. So I made the figures actually probably yesterday. Oh, in any case, so the accelerometers have 3 axes, right? So the chips tend to have 3 axes. We're measuring 2 of them. So the cylindrical tub is nice. It's got the symmetry, so the impact is in the center. So so we can think about radial directions and vertical directions. So that's what I'm putting here. And then the lines, each one is from a different channel, right? So the one closest to the impact has the biggest peak. And then as you get further away, there's much less, acceleration. And then, so this top one, I would call it like a longitudinal wave. It's like a P wave where it's a pressure or a sound wave. But what you can see the travel, so we can measure the travel speed of the pulse, because there's a delay in when you see the blue spike and the orange spike, there's a delay, so that actually tells you how fast it traveled, and it's also dropped. So that means there's a lot of attenuation. It also spreads out. So if you look at the orange one, it's actually wider than the blue one. So we're seeing a lot of effects. So things that when the pulse spreads out, that's like a scattering, where you're seeing scatter. The wave is the energy is not necessarily lost when you spread out a pulse. You can think of it as a diffusive process. But we're also seeing a lot of energy loss because the pulse peaks are dropping. So in this direction, these are the vertical pulses, and I think they're like a Rayleigh wave. So where you see, you can think of this as like a deep water wave, essentially, except that the thing that's giving you, instead of having gravity being the restoring force, it's actually the elastic restoring force in the media. So it's probably like Irradiated. I'm not 100% sure on what it's like. So this is exactly like the previous plot. It's just I'm showing you more time. So in the previous plot, we were only going out to like 20 milliseconds, and now I'm going out to like 80. And the R accelerations don't look any different. There's not much going on. But in the Z one, you see this, you know, up and down type of thing that lasts much longer. So what I'm showing you on the right side, where I subtracted off the bottom one from all the other ones. But and you can see that lots of stuff goes away here. The signal is a lot smaller. So this, and this are really showing the same thing. So what's happening is the pulses are propagating and then they're spreading out. And then at some point, the whole thing is going up and down. And so I think what's happening is pulse diffuses, gets wider, and then it's like a normal mode where the whole thing is doing this. And so so how do you tell that that's going on? Well, we can also put the accelerometers at different depths. And so, you know, when we look to see, are they decaying near the bottom? So I think the pulses get weaker as you go to the bottom. And so it's not a matter of the tub going up and down at the bottom. So it really is the whole material going up and down. So when we first looked at this experiment, we thought, oh, we're seeing the pulses decay. We're going to support the seismic jolt model because we see this rapid attenuation. But actually, we're seeing both phenomena where we see seismic attenuation and then we see a reverberation. So, but now the hard part is how do we scale it to an asteroid? So which part of it depends on gravity? So, yes. In the granular media, one important parameter is the pressure. So if you go down, you have more hydrostatic pressure. When you put your hand inside the granular media, you'll see it's like really hard to move it around. It's like putting your hand deep in sand. Or if you get buried in sand, you'll notice that it's like, it's really heavy and it's hard to move. So hydrostatic pressure gets really high. On an asteroid, you wouldn't have very much hydrostatic pressure. So if you put your hand in an asteroid, it would be really easy to move it around. So how do we compare our pulse propagation to what would happen on an asteroid? So one thing I can do is I can estimate the pulse in the peak, the pressure peak. And if that is high compared to the hydrostatic pressure, then I'm in a regime, it's very nonlinear, and it's the propagation probably depends on the pressure in the pulse, not on the ambient pressure. So I think we are in that regime, and that means this time period where we see this rapid pulse decay is likely to be scalable to an asteroid. So that's good to know. But does the spreading and the attenuation, like how fast that pulse drops, does that depend on gravity? And I don't know yet. And when do we get that transition where it goes from the pulse, a narrow pulse, to this big sloshing reverberation? What sets that transition point? So if we can figure out what sets the transition point, we'll be able to say, yeah, maybe you get both seismic jolts on asteroids and you get reverberation. But the thing that sets the transition will determine if the reverberation is ever important or not. So if the transition depends on gravity, then it's never going to be important on an asteroid. So we haven't figured out the whole story yet. Well, maybe we'll figure it out. So, oh yeah, so you can integrate those pulses and you get velocity fields. So instead of showing you accelerations, these are the velocities in the material. So the velocity is going this way and coming back. It mostly goes this way, it doesn't quite come back. And then the vertical stuff goes up and down, actually. So you can see these are actual velocities, just the integral of the accelerations. So this is kind of what I said. We think our lab experiments are in this nonlinear regime. So that part's good, but we're not really sure how the attenuation is going to scale with G. Oh yeah, so I did get quite good at modeling pulse propagation. So I'm pretty happy with this. So this, when I said the pulse drops and spreads out, that part we can model really well. And so this is the radial components the type of model that does this is advection diffusion. So advection just means it moves with a speed, and then diffusion means it spreads out. And so you can match the first three pulses are matched really well with that type of model. Okay, so kind of summarize all the laboratory experiments that we've got. Impact pulse attenuation is probably rapid, so we're probably going to support the seismic jolt model. But you do get a transition to reverberation. My guess is that it's going to be very low amplitude, so it'll happen, but it won't be really important. It won't be enough to actually move things around on an asteroid. A single pulse can give you boulders on top, so you don't really need reverberation to account for the boulders that are perched on the surface. And impacts, low velocity impacts, lots of them bounce on an asteroid, even when they're small particles. And understanding, so we did our experiments in single size, or not single size, but narrow size distributions. We don't really know what's underneath when you look at one of those pictures. And so people are guessing, what if there are big rocks under there? How would you know? And that's actually something that maybe if you had if you could watch it as something hit it, you might be able to guess what happened, what it's like underneath. So, we could do more interesting experiments with like real mixtures. That might be something we could think about doing. And then this whole issue of how do you model these complicated granular systems in sufficiently to be able to predict what's happening, both in terms of their long-term evolution and for real reasons like, deflecting them or having a lander land on them. We're probably getting better at it. Okay, so are people still with me? Should I continue a little bit? Talk about binary asteroids? Okay, all right. Okay, if you guys are on, because this is a good breaking point if you guys are like, okay, I got at least 2 or 3 thumbs up. Okay, so I'll talk about binary asteroids. So binary, this is going to be kind of different. So this is not us getting our hands dirty in sand anymore. So we'll talk about actually modeling binary asteroids in dynamics. So here's a simulation of the Moshop Spawnit binary asteroid. This is one of the first ones where they actually measured the spin-up rate of the primary from radiation forces. And this particular model is based on radar observations. So they got close enough to here, they could do some pretty accurate radar measurements. One thing you notice is the secondary, that's the little one. It's long and it's always pointed towards the primary. So it's what we would say tidally locked, right? So like, when you look at the moon, the same face always points towards us. The same thing's going on here, right? So they're predicting that it's tidally locked with primary. So I'm going to actually challenge that assumption. It's not that it's and it was long. So one thing that's really amazing in the last like 30 years is the realization that radiation forces are really important in asteroids. So, so we used to think of asteroids as being point masses and all they were feeling was gravity and that was it. But over long periods of time, radiation, because it bounces off different areas of the asteroid, not the same, can actually really affect their orbits. So that's the top one called the R.I.T effect. So you have day-nighttime differences and depends on which direction you get radiation off of compared to the opposite direction. And if there's a lag between the day and the night side, you get a torque that changes the orbit actually. So, and that's a feeding mechanism for, it moves things out of the asteroid belt into near Earth crossing orbits actually. So asteroids that are more affected by the R.I.T effect are more likely to become ones that are in our neighborhood. And the reason people know that is when you look at the size distribution of asteroids in the asteroid belt, it's not the same as the size distribution of asteroids that cross the Earth's orbit. And a nice way to explain the difference is with the R.I.T effect. So the same radiation forces can also give uneven emission and absorption on different facets with respect to the center of mass of the asteroid. And that's called the York effect. And the Y is the same guy, Yarkovsky, and the O, R, and P are a bunch of different other people. Those are initials. And the York effect explains why these asteroids are top-shaped and also gives us a mechanism for fission. So if you have a binary asteroid, the secondary also feels the radiation forces, and that can actually give a torque on the binary, which causes the binary can either go in or out. And one of the real surprises, if you actually estimate how strong is that, so how fast do these things operate? It takes millions of years, but you have millions of years, you know, for things to move around. So with binary asteroids, the problem is that they're predicted to dissolve in like 10.1 million years. So it's like a 10th of a million years, but they're supposed to last longer than that, like by 10 million years. So how do you explain why so many Earth crossing asteroids are binaries if they fall apart really fast? So this is actually a problem in the binary asteroid scientific setting. So this is kind of an old simulation that's showing you by Kevin Walsh, I think, showing the top view and the side view of the same asteroid, and it's spinning up because of York. And the two different colors, the white part is the inside, and then it spins off a bunch of material, goes above the centrifugal limit and actually spins off material, which then eventually collects into a secondary, which so he proposed this as a formation mechanism for binary asteroids. It's kind of a long video, actually. Let's see if I can go to the end. Yeah, so there's the end. So now we have a binary asteroid caused by fission. So I kind of said this, binary York effect. So there's another detail here. Most closely orbiting bodies are tidally locked in the solar systems. Like the moon is tidally locked with the Earth. All the Galilean satellites are tidally locked with Jupiter, where they always point the same direction towards Jupiter. Almost, I think all regular satellites are tidally locked, except the minor satellites of Pluto and Charon and Hyperion. Hyperion's on an eccentric orbit, so it's actually tumbling because of that. But almost everything else is tidally locked. So people are assuming this is tidally locked. So it might not actually be tidally locked. And when you compute the Bi-York effect, what they usually assume is there's two possibilities. They say it's tumbling and there's no torque because it all averages out, or it's tidally locked and the torque is really big and then the binary will fall apart. And there's never any in between. And so what we found is there's actually a continuum in between. And that was kind of surprising to find. So, so I have to show you a simulation. So here's the simulation. So what you notice is this is the secondary, and the long end is always pointing. So I'm in the frame, so that this thing is really orbiting now, but we're in the frame, so it's not moving. What you notice is the long axis is always pointing towards it, but it's rolling. It's like spinning this way. So if you look at the light curve of this, you wouldn't necessarily be able to tell. You'd know that it was mainly pointed towards the primary, but you wouldn't be able to tell that it's rolling back and forth. And so that's mainly what we're seeing in the simulation, that you've got this kind of intermediate state where it looks tidally locked, but it's, you know, kind of tilting back and forth. So this turns out, so there's two big problems in the asteroid setting, and I've already mentioned this one, but the Bi-York effect is so fast that a binary can disrupt, which is in a 10th of a million years, which is shorter than their lifetime. The other mystery in the binary asteroid setting has to do with its material properties. And so people estimate how strong, how rigid. So this mu is like elasticity. So it's how stiff it is. And Q is a dissipation factor. So if mu Q is low, it's mushy and a lot of energy is lost when you deform it. And if mu Q is big, then it means it's really strong and not much energy is lost when you deform it. So there are estimates for what this factor is for single asteroids, and there are estimates for binary asteroids. and they disagree by like 4 orders of magnitude. So either binary asteroids are really different than single asteroids, or one of those estimates is wrong. And the single asteroid estimate is based on how many asteroids are wobbling. So when you have an asteroid that the spin is not aligned along one of the body axes, then it starts to tumble or precess, and it feels a periodic stress strain. And that eventually damps down to where it's oriented, and then it spins. The spin axis is along one of the body axes. So I think I have a simulation. Yeah, this shows you, this is an oblate thing, and the spin axis is vertically, but the body is kind of tilted so it precesses. So that's an example of something that feels a periodic acceleration. Another word for this is non-principal axis rotation, which is the spin axis is not aligned with the body axis. So you think of a Frisbee, if you orient the spin axis nice and perpendicular to it when the Frisbee is going, it's very smooth. But if you tilt it, it kind of wobbles as it's moving through there. So when I showed you the binary asteroid and it was pointed towards the primary and tilting back and forth, that's a type of non-principal axis rotation. And it's, you know, not quite totally tidally locked, but also it's also not completely tumbling in a completely random way. So this is what tumbling looks like. So that's a simulation of Hyperion, which the tumbling is caused by we've related both because the body's not round and the fact that it's in an eccentric orbit. It's not in a circular orbit. So it feels this periodic tidal field, which keeps it tumbling. So this shows you all the different degrees of freedom that you can think about when you talk about spin dynamics. So here we have the secondary, and actually you can see I put a shape model in there already. And so why am I putting a shape model in for the secondary? And that's because I want to actually figure out what's the radiation force it's going to do on the secondary if it's in this funny rotation state where the long axis is pointed this way, but it goes back and forth. The long axis, what you can tell the angle between the long axis and the direction to the primary as a libration. So if you think of an airplane pointed towards the primary, the libration would be like the yaw of an airplane. And then this tilt back and forth that we saw in the simulation, that's like the roll of the airplane. And then you could also tilt the body back and up and down with respect to the direction to the primary. And that's called pitch. But I would call it long axis inclination because it's with respect to the orbital plane. But yeah, keeping track of all these angles is challenging. So it's one of the things, you know, I get the simulation output and then I have to say, what do I want to plot? And then, you know, figuring out what to plot is half of the half of the thing that makes the problem hard. So this is this shows you the output of one of the simulations. And so in this particular simulation, I'm letting it tidally spin down. So if it were like the moon, it would tidally lock. And you can see this top picture shows you the spin down, and it is dropping. But then this shows you the tilt, the short axis tilt, and that's when it's doing this. And so there's this really long period of time where it's rocking back and forth, but at the same time, the long axis is always pointing towards the primary. So I don't think people expected this to be long-lived, and I don't think anybody had actually ever looked at a simulation to see. But if we take this output and then say what happens to the biorb torque, while it's doing this, there's very little biorb torque. And then when it's down in this area, we still have some back and forth, then the biorb torque is less. And so really it gives you this continuum behavior. So you don't just have biorb is off when it's tumbling and on when it's tidally locked. You have this great, you know, slow increase of how much torque you get. So if asteroids spend a lot of time in this state, then they're not going to fall apart because of radiation forces. So this is why I'm predicting that if people start looking at binary asteroids more carefully, they should see that they're in these non-principal axis rotation states. They should see them tilt back and forth. And there would be a selection effect. So supposing an asteroid actually spins down and tidally locks, and then the torque starts making it fall apart. Well, then you're not going to see it because it's fallen apart. So the fact that we see so many binary asteroids is telling you that most of them have to be in this state because it's a way to keep them from falling apart. It's like the selection effect in some sense. Yeah, so let me show you our predictions for the BIORB. I'm going to skip ahead a little bit here. Yeah, so here, in order to actually predict the effects from radiation forces, what we have to do is sum over the force on each one of these little facets. So I used a bunch of shape models. And then in our simulations, this shows you the actual prediction along with the non-principal axis angle. And you can see in the beginning of the simulation, it showed going back and forth, but averaging to 0. And at the end of the simulation, when the non-principal axis rotation amps down, it goes all the way back up to the value that you would predict if it were tidally locked and not rocking back and forth. So let me summarize. Yeah, so previously, people had these two states, and now we have this continuum that depends on spin state, and this feeling that this understanding that maybe these intermediate spin states are long-lived in the binary asteroid. So one of the reasons I was, why? So if I look at something that's a similar shape, so our secondaries are actually similar shape to Phobos or Deimos. But when I ran simulations of Phobos and Deimos, they didn't do this. So why? And the difference is Mars is round. I mean, it's not exactly round because it's got Olympus Mons and stuff, but it's really close to round. But the primary is a top shape and it's got lumps on it. And the secondary is also quite not round. And so when you look at how near they are to each other, they're quite near. They're feeling this very complicated gravitational field because they're not round. And that's giving you extra perturbations in the problem. It's making the spin dynamics much more complicated. So I think that's the reason why nobody really expected them to be so complicated. So to summarize, non-principal axis rotation in secondaries is long-lived. And if it's detected, actually this does resolve one of the problems with material property discrepancy. And it would help explain how they could last long enough to, make sense out of the statistics in the sense that many binary asteroids are actually secondary. They're actually binary. Many asteroids, many NEAs are actually binary. That's what I meant to say. And lastly, we're predicting that secondaries and binary asteroids are in these complicated rotation states right now. And so that's like, hopefully we'll be able to find out if that's true. I'm not sure. If it's not true, then we'll have to come up with a different theory, or different explanations for how they managed to not fall apart. But for the moment, it's a prediction that when they get to DART, that DART mission gets to Didymos and Dimorphos, that secondary should already be in a complicated rotation state. So to contrast, when we finished our paper, I posted it on the archive at the same time, right? So just before ours, the DART team posted a paper where they were modeling the impact. And they concluded that in the impact, it would excite this type of rotation state. And we were like saying, no, it's already in it. It's like you need to know that it's already in this complicated rolling state, because I don't think it has time to get out of the complicated rolling state, this roll. But hopefully the DART mission involves an imager that the Italians are building, and then there's a European mission that's supposed to come a year later or so to take pictures of what actually happened. So hopefully there'll be enough information to see whether this prediction is correct. Hey, because I think I kind of got to the end. I think I'm going to stop there, but hopefully this gives you a feeling for what is soft astronomy. So soft astronomy. So thank you. Questions? Yeah?
We've now orbited these things. When we orbited the moon, we found mass concentrations. Effective gravity.
Yeah?
Have we been able to find out anything about what's inside these things? Or is the shape too complex to?
So in the ASRAS mission, I mean, they were looking at it for a couple of years, and it was really convenient that particles came out of Bennu. So they were tracking lots of particles, and that gave them a really good gravity model that has like up to 10 multipolar coefficients. And so they asked exactly that question. It's like, how homogeneous is it? And I think there are some big enough deviations in the multipolar coefficients. They think it's got clumps inside, but it's pretty hard to figure out exactly. So they had a bunch of models where they were saying, oh, we could put this big clump here and that might work to match it. But yeah, I think they did come up with a pretty strong statement about it being inhomogeneous density in order to explain the gravity coefficients.
So that might be different on a different body.
Yeah, yeah. So with Didymos, so Bennu, they've been orbiting it for a long time, and it's not just the orbit. They had to understand the gravity field quite well to achieve, because it's not a very strong gravity field, to actually stay in the orbit. But then when they were tracking all the other particles, they just got way higher precision in all the gravity coefficients. So with Didymos and Dimorphos, the DART mission isn't going to spend that much time there, so I don't think they're going to get quite the same gravity information. So then they're trying to slam something into it. They're going to hit it with something. So that's a different kind of study. Yeah, it would be nice to have more, or it would be nice to be able to drill into one, or put a seismometer on one, right? Because there are lots of ways you could get information about what's underneath. There's a little bit of information about thermal inertia and stuff like that from.
I mean, we haven't successfully landed on one yet.
Oh, well, so the mascot bounce. So it's not the first. I can.
Well, yeah, we put them on there, but
yeah.
something happens.
Yeah, no, nothing's really like driven around or anything. It'd be nice though. You could you could make a little robot that did a lot of bouncing in a low G environment. It's a really low G environment. So, yeah, question.
So, in the first half of your talk, what you were looking at was what happens when you have various impacts, and you have this sorting effect, which can potentially explain larger objects, large boulders, large features on the surface, and all the fine powder, for example, just down to the center. And we use maybe I've interpreted that kind of the way the experiment was to show how you end up with large pieces on the top and smaller things settling down underneath.
Well, yeah, so we were just hitting this bucket and it goes up and the big things wind up on top. You can also get things on top if you have a landslide. So some of the pictures recently from Bennu have been interpreted in terms of surface flows, like they see, if you look at a mountain, sometimes all the boulders seem about the same size in a landslide. And so, or they see rocks on top of other rocks. So there's a big catalog actually by, I think it's Eric Jawi. She put together, so it's all just by, she just took pictures and made a list of things she thought were evidence for surface flows. And so we were curious too, like you don't have much room on an asteroid for things to move. So what kinds of surface morphology can you get with small landslides?
Well, that was going to be my question.
Yeah.
Dovetailing with the back
Yeah.
of your talk, which was, you have this non-uniform spin-up period where you're spinning up and then you have the secondary form.
Yeah.
But I can imagine there being sort of this soft sifting effect just because you just very gently are perturbing the distribution, and eventually these things might settle up on their own.
Yeah, so
Having a large shock.
So one of the big mysteries has to do with the porosity. So that they do know the densities of these things, and it's quite low. It's like 1.5 or something like that. But they're probably, they're not made, rock is denser than that. So how do you explain why it's so low? So one way is you can have a lot of holes in it and then things would sift. The other way is you have rocks that are just really porous, what they call microporosity. And I think right now the picture of microporosity is winning. but it also confuses the thermal inertia and the radar measurements and everything, because people aren't really expecting the rocks to be like, you know, really low, like foam. So, but yeah, I don't know if things really sift down. So with the Hayabusa, with the Itokawa images where they have this rocky stuff and then these really smooth regions, that is probably what's going on, because what they did is they mapped the low, like the downhill areas, and the downhill areas all tended to be smooth. And so that really is a good picture for Itokawa. I'm not sure if it's a great picture for Bainey. Do we expect the center to have boulders, or do we expect the center to have lots of little dust? I don't know. That's a good, yeah. Maybe, I'm not sure. Do people in the CIRUS-REx mission have a strong opinion about that? I don't know. I know the microporosity, macroporosity is pretty heavily debated right now. And then, yeah, so because there's so many conflicting bits of evidence on it. So, yeah. More questions? Everybody gonna go home and play in Granular Systems, because I can waste a lot of time with my breakfast cereal. Yeah, question in the back.
You mentioned that the dark came up for the
Oh yeah, well they just
why do you think
they just like everybody, they assumed it would be tidally locked in the beginning, and then they said, okay, now we need to predict what's going to happen after the impact. So they they hit it, they gave it a momentum change, and then they said, what is it going to do? And the cool thing is they saw that same rotation state as we did, where it rolls back and forth. So when we were looking at there, it's like, we thought we were crazy saying this is what's going on, but they found the same rotation state. So they were saying that after the impact, it would be in this rolling rotation state. But we're saying it can't ever get out of that. It takes a really long time for it to leave that rotation state. So it's more likely that it's currently in it before the impact. So we were studying the evolution of the system, not trying to say what would happen after the impact.
So is it possible that dark could actually kind of bounce off of it if it's already rotating?
It's a high velocity impact, so no. So we're not shooting guns into our, there are people who do that, but we don't have a high velocity thing. Yeah, question?
So the dark will be taking pictures of the system as it approaches over a period of some months and weeks.
I hope so, yes.
Have you checked to see if they could answer the question, if it's really tidally locked or is it oscillating?
Yeah.
By looking at the pictures that you
Yeah, I've let a couple of people know that I'm curious about this.
what's the time scale for the oscillations? Days, weeks, years?
So it tends to be a little bit slower than the rotation period. The rotation, so if it's tidally locked, the rotation period is like half a day. And so it takes a couple days, but that would be within, it would be within the length of time if they had, and when they come in the orbit, they should maybe, particularly the Italian imager, because we see a cube experiment, may be able to get good enough data. It's not necessarily the only binary asteroid. I mean, like the Mashap Squanet one, they have great radar data. So it's possible that other binaries will get close enough where they could analyze the light curves well enough that they might be able to tell the difference. So it's not necessarily the only way to look, but yeah, I'm definitely curious. I let them know. We'll see. They're aware, I think, at least some fraction of them are aware. It's a pretty big team and they have a whole lot of other things. So a lot of what they're focused on is the momentum transfer efficiency, because that's relevant for planetary defense. So they're less interested on whether it's doing some wacky spin thing than they are about how. So the momentum transfer, if it blows a lot of material out backwards, then you get a different momentum transfer than if you don't. So predicting how the body, how much it gets pushed by this particular impact is part of what they're the main thing they want to know, actually. But any other questions? Well, if you think of more, don't be shy.
Thank you very much, Alice.
You're welcome.
Cool stuff.
Yeah.
Look forward to Dart launches next month, right?
Yeah, it's really soon, yeah.
It's
yeah.
16th or
yeah.
something. Look forward to that. Great. All right, folks. So that's our meeting for October. Next month, we're having elections here. We also got a bunch of events coming up. So tomorrow there's open house. I don't know that viewing looks really good tomorrow night. It looks pretty cloudy, but we'll play that by ear. So there's member observing if it's clear tomorrow night. Questions for me?
How about the Sunday? Sunday.
Go out anytime you want. Just that we'll have an official event typically tomorrow night. Dave, you guys, if you're interested in going to Applebee's afterwards, we can head over there, have a appetizer or a soda or something. Any questions for me before we leave? Online, anybody? Let's see if we got comments down here. All right, thanks, everybody. Have a great evening. Thanks for coming.
An asteroid